Okay, so welcome to Zoom. Today is September 13th. We have a question for 2.5, number 8, which is a derivative question. There's an associated question that's come up through the chat. It says this might, between the definition of the derivatives, the product and quotient rules, now we have the chain and implicits. How are we supposed to know which ones to use on which problems? They are all scaring me. Good question. All right. In fact, I could probably partially answer your question with this one. So I'm going to share the screen. Actually, you know what? I'm going to do a different camera here. And then I'm going to pin this. Okay, so this is a derivative question. Uh, you basically just tackle them as you see them. This one clearly is written as a product, so we're going to have to use the product rule. There is no really way around it. You can sometimes do algebra to avoid a certain rule, but in this case, I don't really want to foil all that out. So we'll just take it as we see it. In regards to the chain rule is actually present in every derivative that you do, every single one. In the trivial cases, it's usually just one, but it is present in every derivative. And part of the skill in differentiation is not so much learning just the process, but also learning when to use them. And that's I think that addresses the question that came up. Is that you have a whole bunch of tools now, and you through experience have to kind of figure which is the best approach. Um, let's work this one. What I would suggest you do is, well, it's going to be the product rule. Stuff in my paper there. And I'm going to leave myself a whole bunch of space because it's going to get lengthy here real fast. I'll put the first one in. So it's first derivative, second, plus the second derivative times the derivative of the first. So we have first. So I'll just copy it in. I don't really care about appearances. And then the second, I take the derivative. So I bring the 9 down. This one's going to involve the chain rule. So I use the power rule to bring the 9 down. I don't change the base. That's a minus sign right there. And then I make the new power 1 less, so it's 8. Now I do the chain rule. The chain rule says do the derivative of the inside and attach that. So it's going to be a 12x. Okay. Now in the second, I just, again, copy this in place. No changes. And then we're going to do the derivative of the first. Same deal. It's going to be a power rule with the chain rule. So the 7 comes down. You get negative 9x squared plus 3 to the 6. And then chain rule says take the derivative of the inside. That's going to be negative 18x. And I hope you can read that. Um, and frankly, stop. This is good enough. Okay. It's not really, I don't think it's worth your trouble to try to simplify this because it will be accepted by the system. And there are, in fact, you will see in probably a week or so, you'll see another method of differentiation using logarithms that actually makes this kind of derivative a little easier. Um, so I would just leave this alone. Yeah, so yeah, he was saying I was trying to simplify, and I think that's what messed me up. I agree. This thing we would actually spend more time simplifying than doing the actual differentiation. And I consider this good enough. Now, most application problems aren't this fancy. And usually if you've got less complicated bases and stuff, usually the simplification then is not that bad and you should probably do it. But in a case like this, yeah, I just want to be able to see that you know what you're doing, you know to do the chain rule, for example, here and here. And I would consider this a good answer. Okay. Let's take a look. There was some questions like for number, same section like 6, 11, 14, and 17. So I'm going to go to the affinity again. Let me just maybe look at number 6 here. Yeah, okay, I'll copy 6 now. 6 is, yeah, I'll share the screen temporarily. Um, there you go. So number 6 is this thing, and Let me just copy. We've got y equals cos cubed, y equals cos times tan, I'm sorry, cos of tan x, y equals tan x. And then last one is sine x tan x. Now, this one has a little bit of a curveball. In fact, it's going to be part C. You know what? I'll tell you what, I'll come back to the visual here. Let's just work out the derivatives. So I'm going to unshare the screen. Got my functions. I'm just going to do them the good old-fashioned way. This one's a power rule. Bring the 3 down. Leave the base alone. Reduce the power by 1. Now you do the chain rule. The chain rule is derivative of the base, so the derivative of cosine is sine, negative sine x. And that's a good answer. The only thing I would do is, since it's such a trivial move, is move the negative to the front. But that's about it. Okay. Um, let's do this guy right here. It's the derivative of cosine, which is negative sine, and then you leave the inside alone, so negative sine of tan x. This is not multiplying. This is the cosine of tan x, not the cosine times tan x. So we do the derivative of cosine, which is negative sine, and then we have tan x here. And then we follow that with the chain rule. The derivative of tangent is secant squared, and that's one you should know. That pops up a lot later classes. In fact, we just kind of answered the question. Let's do that right here. Derivative here is secant squared. And then the last one is product rule. Now I might ask myself, is there a simplification? And I'll do it down here. If I were to do it's sine x times and then tan is sine over cosine. And well, that gives me sine squared over cosine. And you know what? I don't really feel like going down that avenue because that's going to require the quotient rule. So I'll tell you what, it was worth it. It was worth a look, but it's not really worth pursuing. We're just going to work this out. This is a product, sine x times tan x. So the derivative will be the first, which is sine x times the derivative of tan, which is secant squared, plus the second, which is tan, times the derivative of sine, which is cosine. And those are our answers. Now, this problem, they're trying to trick you. I hate it when they do that, but they do that sometimes. Let me go back to the question here. If you look carefully, the first one is A. So that one's, the first one I wrote down is A. Then you have a couple that look kind of funny, like where'd this 1 plus tan squared come from? Well, that's actually secant squared. So it's also can be written 1 plus tan squared. Now, I'll be honest with you, I kind of find a question like this to be a little annoying because it's kind of unexpected, but kind of roll with the punches for this one. Let's see what other weird stuff we got going on here. It looks like D would be the second one here because secant squared is the same as 1 over cosine squared. And then I guess B would be, um, yeah, that would be B after you make some replacements. But you know what? My personal feeling on these kind of questions is if you pretty much stick with sines, cosines, and tangents, and the only exception being when you get secant squared for the derivative of tangent, you're going to be good to go. I would consider these what are written here. Let me unshare. I would consider the ones that are written here good enough. Okay. I think the purpose of that question was also to make you review a little bit of your trig identities. So I'll admit I don't like that when that happens, but so I'll pause here for a moment. Any questions on the couple that I've done so far? You can pop in audio or you can, let's see. Laura had a few questions for 2-4. Um, and then I'll tell you what, let's take, since we have 2-5 up, there's also the question regarding 11, 14, and 17. I'll look at them. I maybe won't do them all, but I could at least verbalize. So I'm going to share my screen. Here's number 11. on 2.5. This is a case where you're going to have to use the quotient rule. There's no way to simplify this. And in a case like this, I would kind of do like I did with that first example. I would just write a whole bunch of parentheses, fill in the blanks, and then leave it alone. Okay. Um, when you get to the stage where you do the derivative, I'm sorry, the bottom squared, well, okay, you can take care of that because that just squares away the radical. For number 12, just power rule, bring the 5 down to the front, leave the base alone to the 4th power. And then you're going to multiply that by the derivative of the base. Well, the 9 just drops out to 0. This actually involves the chain rule too. So you're going to bring the 2 down, 2 cosine x to the first. And then the chain rule again times negative sine x. 14. In the first case, use the product rule. Now, what happens in this case is that you're going to get a bigger, you're going to actually get a pair of products. So when you do the second derivative, you've got to actually do the product rule twice. And unfortunately, there's no easy way around it. You're just going to have to battle it. Then 17. A Cepheid variable star. Let me read this one. It's talking about brightness of a star at time t. So for the first part, find the rate of change of the brightness after t days. Just take the derivative. Let me copy that one down, and maybe I'll do that one. So 2.5, number of 17. The function is b of t equals 2.1 plus 0.4 sine 2 pi 7t. And we want to know the rate of change and the rate after 1 day. Okay. So the rate of change is just the derivative. So derivative of 2.1 is 0. Here we have 0.4 cosine 2 pi 7th t. Then I have to do the derivative of I'm sorry, I did that. The derivative of the 2 pi 7 t, which is just 2 pi 7. So that's the chain rule. Okay. Now, if you want, you can bring the constants together. In this case, I'm just going to use my calculator to get a decimal. So 0.4 times 2 pi divided by 7 works out to be about 0.359 cosine, and then the rest just follows. That's part A. For part B, you just pop in the number 1. Times 1. You just make sure you're in a radian mode. Come on, there we go. So I'll just do it real quick. Give me a second here, typing in 2 pi over 7. I get 0.224 about, so it rounds up. And the units on that, I don't know what the units would be on that one. That would be, I don't know what they use for brightness. It would be something per day. How about brightness per day? I know that's kind of funny, but that's all we got to go on. All right. Ah. All right. Again, I'll pause. Any questions on those? So Jorge Hernandez says on number 11, he brought the radical to the top as a negative 1/2 into the product rule. That will work. That will absolutely work. Let's take a look at 2.6. 2.6 number 1. Give me a second to find it. Alrighty. Let me share the screen. Here's 2,6 number one. I'll copy it. The function is 5x squared plus 2x plus xy equals 3. And we're told that y of 3 is negative 16. And then we want to find y prime at 3. All right, let's do that. There you go. We're going to do this implicitly, which means we're going to do each derivative in place. Now, you know what? This is a case we actually could solve for y. There's only one y in there. But I don't know. We'd be getting into a quotient. And this isn't that bad to do implicitly, so we'll just do it implicitly. So in each of these arrows represents a derivative. So we're going to take the derivative with respect to x of each of these terms. Derivative of 5x squared is just 10x. Derivative of 2x is just 2. Derivative of xy, that's a product. So we're going to do a product rule. So it's going to be first times the derivative of the second. And this is where I have to write y prime. Because the derivative of y is 1. And the chain rule kicks in and says, okay, what's the derivative of y? Well, it's y prime. Plus the second, which is y, times the derivative of x, which is just 1. Technically, that's dx, which is 1. And then the derivative of 3 is 0. Let me clean this up just a tad. And normally what you do is you isolate the y prime. So let's get everything that doesn't have a y prime to the other side. And then let's divide by that x. So everything is isolated now. Now that's the derivative in generic form. Now we come back to the initial condition. We're told that y of 3 is negative 16. That just simply means that x is 3, y is negative 16. So we pop the numbers in place. So y prime at 3, we put in wherever there's an x of 3. So that's going to be negative 30. Take away 2. And then wherever there's a y, put in a negative 16. That'll make a plus 16 because we got negative y. And on the bottom, we have x again, so it's 3. What does that give us? Negative 32 plus 16 is negative 16. We get negative 16 thirds. All right. Does that help on that one? Again, if you don't be shy. We have a question here for 2,6 numbers 5 and 7. By the way, if you want to see this again, just ask me. I can just put the paper back up on the screen. 2,6 number 5 and 7. Let's see what's going on there. Okay, number 5 is number 5 is another one of those. It's just a little more complicated, but it's not bad. Let me write it down. 2.6 number 5. It's 7xy to the 9 plus 6xy. This will be a good excuse to talk about chain rules and stuff. Equals 13, and then we're at the 0.11. So that happens last. All right. What we want to do is well, x and y are connected by multiplication, so we got to use the product rule. And I think what I'm going to do is I'm going to move the 7 out in front. It's just less confusing. I'll do the same thing with the 6. I'll just kind of kick that out to the front. Now the derivative of 13 is 0. We're doing derivatives here. This line here is going to be the derivatives line. So remember, I'm mentally ignoring the 7. So I'm just worried about the x and the y to the 9. So it's first, which is x, derivative of y to the 9, which is 9, y to the 8th, chain rule times y prime. Make that stand out. And then you do the second, which is y to the 9. And we're not taking the derivative of y to the 9 at this step, so we don't have to worry about dy dx, times the derivative of x, which is 1. Same thing here. First, which is x, times derivative of y, which is y prime, plus the second, which is y, times the derivative of the first, which is 1. And we're asked to find dy dx at 1, 1. I'll tell you what, I'm going to go ahead and simplify. I'm going to distribute the 7, so it's going to be 63 x y to the 8th times y prime. And then the 7 comes here, that's going to be 7 y to the 9. The 6 gets distributed here, it's going to be 6xy prime. And then the 6 gets distributed here, which gives us 6y. And the 0 is just hanging out doing nothing. I'm going to solve for y prime. So what I'm going to do is I'm going to collect the terms that have a y prime and group them. And then I'm going to move the terms that don't have a y prime to the other side. They become negative. Subtracting. And the last step is to divide out by the parentheses here, and you get a big old ugly fraction. And you write it down. Okay, that's the derivative. Now I haven't answered the question yet. To actually answer the question, I got to put in the numbers 1, 1, but I'll do that here in a second. But more importantly, make sure you understand how the derivative was found. There's a lot of stuff going on here. We've got the product rule appearing twice. The chain rule is kicking in whenever we do the derivative of the y part. And then, of course, there's a lot of algebra just to keep track of. And I think you're probably discovering in this class is that you're going to become really good at your algebra because you're doing so much of it. You really have no choice but to improve. Anyway, at 1 and 1, we just put the numbers in. And actually, that's easy enough. We can just do that visually. So negative 7 take away 6 is negative 13 on top. And then everything is 1, so 63 plus 6 is 69. And that's good enough. Yay. All right. And I don't care if you don't reduce your fractions. And that doesn't reduce. All right. That's good enough. All right. So I think I'm kind of lost track here. RJ wants to take a look at number 7. I'll do that one here in a second. This was number 5. And again, hop in. If you got a question, just jump on in. All right, let's take a look at number 7. I wonder what that's all about. I hope it's easy. Oh, this one. All right, famous question. Let me copy it down. This is number 7. This is an interesting curve. It's called the lemniscate. Looks like a figure 8. Looks like an infinity symbol. And we're given the point at 3, negative 1. Okay. The equation of the tangent line to the lemniscate is, we want the equation of the tangent line. So we don't want just the slope. We want the actual full-on equation. Well, of course, to get there, we need the slope. All right, so that's going to be the main challenge. All right, so now I'm going to show you something, a little tactic that I think might be helpful here. Let's perform the differentiation. Got to do the product, I'm sorry, blah, blah, blah. The power rule, bring the 2 down, so you get 4. Base stays the same to the first power. Now we do the chain rule. Now we do the derivative of the base, which is x squared plus y squared with respect to x. So the derivative of 2x, I'm sorry, x squared is 2x. The derivative of y squared is going to be 2y times y prime. Okay. And again, make sure that stands out. You don't want to miss it. and then equals, and then 25. I'll do the same thing I just did on the left side. I'll take the derivative. You see it's going to be 2x, take away 2y times y prime. And the y primes appear because of the chain rule. Okay. Now we need um, y prime. We need to solve. But I'll be honest with you, this is going to be ugly because you're going to have to do a binomial multiplication here. So a neat little maneuver you can do here is go ahead and pop in the numbers right now. And this will actually greatly simplify the question, believe it or not. If we put the numbers in now, so wherever there's an x, put a 3, and wherever there's a y, put a -1. Uh, put in x equals 3, y equals -1 now. That actually is going to make the problem a lot easier. Watch this. So when I put a 3 in for x, I get 3 squared is 9. 9, I'll write it out. 9 plus the -1 squared is 1. And then I've got 2 times 3, which is 6. And then I have 2 times -1, which is -2. And then, of course, the y prime is unknown. You have to figure that out. Then on the right side, same thing. I've got 25. 2 times 3 is 6. And then I've got -2 because y is, actually, that's going to be a +2. Y is -1, makes that a plus. And blah, 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 y prime. Okay. So I've got myself some, I guess, gentler looking numbers here. I still have to isolate y prime. Still got some work ahead of me. But this is actually 9 plus 1 is 10. 10 times 4 is 40. So I really have 40. If I distribute that, I've got 240, take away 80 y prime on the left side. And on the right side, 25 times 6 is 150 plus 50 y prime. And then now it's looking a lot friendlier. You know, that by putting in the numbers early, you reduce the amount of just tedious algebra that you have to do. So let's go ahead and let's bring the 150 to the left side. So subtract out 150. You get 90. Then add the 80y prime to the right side. And you get 130 y prime. So therefore y prime is 90 divided by 130, which is 9/13. All right, that's the big crux of the problem. That doesn't answer the question yet. We still need the equation of the line. This is that old formula from algebra, but we've got all the ingredients. Now, this was a lot of math, and I'll pause here if there's anybody who has any question on any step. Okay. All right. Well, let's go ahead and proceed. We want to find the equation of the tangent line. That's the slope, 9/13. Just trying to stay afloat. Fair enough. And then we got x is 3, y is -1. So you just pop the things in there. So y minus -1 equals 9/13. X minus 3. Y plus 1 equals 9/13. I'll distribute that 9 as that's going to be minus 27/13. And then when I take away 1 on both sides, gosh darn, I have to do fractions now. That's going to be -40/13. And that's our answer, and we get a happy face for that. Okay. By the way, there was a question in ed discussions pertaining to this question, but it had to do with the show me when you click on that and Infinity. Be aware that everybody's problems vary just a tiny bit. There's a little bit of randomization going on, but sometimes the show me or the help part or the key or whatever you want to call it is only written for one of the questions. So you're going to see a bit of a mismatch there. Hopefully that's not too confusing. You can make the mental adjustments as you go along. But yeah, that question did come up. All right, let's catch our breaths here. So when you're doing a question like this, expect a lot of algebra, expect a lot of work, but it's good. It's like, I guess you'd call it algebra gym. Um, there's just no easy way through. You just got to roll up your sleeves and dig into it. All right. I don't know. Have I overlooked anybody's questions? I mean, I'm going through the chat here. I've been going kind of quick here. If you have a question you want looked at, I can review a question we just did, or I can do a new one. Um, Anything you want. Whoever pops in first gets to tell me what to do. I'll make up one. Let me just make up a question that has the chain rule because the chain rule is present in every derivative. So let's do a brief discussion on that. It's in every derivative, but a lot of times it's a trivial step and it's not written. So I'll give you an easy case. If your function is, let's say, how about y equals x cubed, the derivative would be, you're doing the power rule here. You bring the 3 down, 3x squared, 3x squared. All right. And then normally you stop. But in truth, there's actually one extra step. You actually have to worry about the derivative of the base, just the base, not the x squared, but just the base. And the derivative of x by itself is 1. Now, there's no reason to write that extra 1, so we don't. But I want you to know that it's there. So then I'll say harder. Suppose I take a question like y equals, how about 2x squared plus x plus 1 to the third power? Okay. Well, this is a composition of functions. Basically, it's a function inside a function. And that's where the chain rule really has to be used. So you're still going to use the power rule in this case. And basically, you work outside in. So you work the power rule. So basically, it's something cubed. Bring the 3 down, just write the base without any changes to the square now. Okay, that takes care of the outer derivative. That's the power rule part in this case. Then the chain rule is invoked. It's always multiply. Now, whenever you have more than one term, put some parentheses on, and then you just perform whatever derivatives you have to do. So derivative of 2x squared is 4x, derivative of x is 1. This derivative of this one is 0, so I don't need to write it. And that's good enough. That's a good answer. Okay. And then let me give you, I'll say hardest, but it's not that bad. Let me give you a case where we might have a nested. Yeah, somebody has a question. All right. Suppose you have like, I'll make up a weird one. How about you have x squared plus sine of 3x to the fifth all to the fourth. Okay. Um, well, you just work outside and just kind of take it bit by bit. So this whole thing to the fourth power, bring down the 4, write the whole thing without any changes to the third power now. Immediately now start your chain rule on the base. Derivative of x squared is 2x. Notice I have a parenthesis started here. Now this gets fun. The derivative of sine is cosine. And then I have to just leave the base as, I'm sorry, the argument as it is 3x to the 5. And then now we've got another chain rule. This is going to be 15x to the 4. And so this one had a chain rule, I'll call it chain 1, and this one had chain 2. And I'd leave that one alone. That looks good. Can I do an example with radicals? Sure. So the chain rule is present in every derivative. And since I've got this up, let me just mention here if you had implicit, because we've done a couple of those so far. But if you had like, how about x squared plus xy cubed equals y? Um, I'm doing this with respect to x, so I'll just take the derivative with respect to x. So derivative of x squared is 2x. Now, of course, chain rule says there's a 1, but I don't write that. Here I have to do a product rule. So first times derivative second, 3y squared. The chain rule kicks in. The derivative of y with respect to x is y prime or dy dx. And then I have to do the second, which is y cubed derivative first, which is 1. And then this guy's derivative is y prime. That's actually the chain rule because it would be 1 y prime. And then, of course, you just, I'll go ahead and complete it. Bring your y primes together. So I'll tell you, I'll move the y prime to the left. And I'll scoot the other guys to the right. And finish it off. There you go. Okay, so that's a case where the chain rule is combined in with the implicit. And let's do one with a radical. Let's do, how about y equals square root? Just make one up here. How about square root x to the 5th plus tan x. Let's throw out a trig in there. Okay. The square root derivative, I recommend that you memorize it. It's always going to be 1 over 2 radical the inside. Okay, that's the short form. Now you can get that just by doing the power rule. Bring the 1/2 down, negative 1/2, and so on. But this one is so common that you might as well memorize it. Now the chain rule, we have to do the chain rule of what you see there, and that's going to go right here. So the derivative of x to the 5 is 5x to the 4. Pardon me. Derivative of tan is secant squared. And that's pretty much our answer. The only thing I might do is, in a case like this, I might compress it into a nicer looking fraction. So I'm not really simplifying. I'm just, I guess you could say I'm doing some cosmetic editing here. And that would be the derivative. Just brought it together. All right. That help?
Yeah, a little bit.
Okay, is there anything you want me to expand on?
I kind of seen like different examples on the videos, the homework of like where to stop on a derivative. So where would be a good stopping point when you're finding a derivative?
Well, you work progressively outside in, and there's only so far in you can go. I mean, if you go to the simplest case, once you've taken the derivative of x and you get 1, you're done. There's no more in to go.
Mm-hmm.
Okay. You just keep on taking derivatives until you can't go anymore. So in this second example here, I worked the derivative of the base. I get 4x plus 1. Well, now technically, I should have done a chain rule right there, but what does that give me? That would just be an extra 1. And, we don't write that. So I'm done. There's no more to go. This one actually had a nested chain rule. There was a chain rule inside the bigger chain rule. Okay, so I had to worry about this derivative here, which was that. So I guess that's how I would see it. Like on this one, if I take the derivative of tan x, I get secant squared x, but now technically I'm supposed to worry about the derivative of x because the chain rule is present, is happening right there where my pen is. But that's going to be a 1, and we're done. All right. Let me share the screen here. 2.4 number 13. This one is just kind of troublesome because it's messy. The function is rad x on the top and 8x minus 8 on the bottom. We want the equation of the tangent line. So that we don't want just the slope, we want the full equation when x is 2. This just gets messy. Check this out. When you put in when you put in 2 for x, you get radical 2. And on the bottom, you get 16 minus 8, which is 8. And one of the suggestions I put into the ed discussions was don't even mess around with the radicals. I'm going to immediately turn that into a decimal.
Can you change it to your so we can see your screen?
Oh yeah, I forgot to do that, didn't I? Yeah, thank you. Sorry about that. All right, so I'll just review here. Here's the function. We want the equation of the tangent line when x is 2. When you put a 2 into the function just to get the y value, you get rad 2 on top and you get 16 minus 8, which is 8 on the bottom. And my suggestion is to just get a decimal value right now, because if you try to keep it in this format, it starts to get real messy. Now, when we take the derivative, we have to use the quotient rule. So I'll write it out in all its ugly glory. So let's do it. Bottom, derivative top, minus top, derivative bottom, all over bottom squared. Okay. Now, the question wants the equation of the tangent line. And this will give us the slope. So we have to plug in 2. What you don't need to do is simplify this. We just need to pop in a 2. It's going to be messy. Let's go ahead and do it. We're going to get 16 minus 8 is 8. 1 over 2 rad 2. Then we have 8 rad 2. And on the bottom, we have 8 squared, which is 64. And you can see how ugly it is, right? So I'm going to work this out on my calculator right now. So the first one is going to be 4 divided by rad 2. And then minus 8 rad 2. And then divide all that by 64. And I just get a number, negative 0.1326. I round it. Okay. I think I looked at the like the key and the affinity, and they're actually keeping the numbers. They're simplifying a little bit, but they're keeping them in this format. Well, that's just a nightmare, isn't it? I think it is. Anyway, we get our formula from algebra for the equation of a line. Sorry about that. Let's see, we got y was this guy number here, minus 0.176. I'll round that to 8. We found our m just now is negative 0.1326. And then we have x minus 2. And then really just need to work that out. Let's multiply that by 2. I'm going to screw that up, so I'll use my calculator. 0.2652, the negatives cancel. And then I'll add the 0.1768. And your final answer should be that, I hope. Okay. And that's good. In fact, it should be accepted. If you keep the decimals, say rounded out 4 places, you should be good enough. Again, yeah, I personally would not feel beholden that you have to keep it in its nice radical format. Just get a number like we did right here, and just deal with the decimals, because it's certainly a lot faster. This question made you cry. I'm sorry about that. All right. We got about a little under 10 minutes. Anybody have any, like, well, I don't want people crying in this class. I want you to be happy. Nah, I understand. Um, Thinner from beating our heads against the wall. Yeah. Well, you guys you're doing the right thing. You just gotta keep working at this. There's really no easy way. I guess learning calculus is like learning any skill. It takes a lot of practice, and you hear about, you hear tutors will say, "I'll teach you all the tricks your professor doesn't show you." Well, I'm showing you all the tricks, and it still takes a lot of work. So you just have to kind of work at it and just be patient with it. Um, if you can, do work at it hard for like an hour, and then don't do anything for an hour. Let your mind rest. And I thank you for your feedback. I appreciate that a lot. And then just kind of, math is like, it's again, it's like chewing on a piece of a $2 steak, as they say. It's just kind of be patient with it, and don't get frustrated. And when you do get frustrated, close everything down, go for a walk, and then come back to it a little later. That's my philosophy for the night. So I hope you guys are doing well and enjoying wherever you are. I hope the weather's good for you. It's still hot where I am, but it's starting to get nice. So hopefully you guys too. Quick question: actually, you know what? You want the final exam to be 40%. Trust me on this one. It's actually worked well in my previous classes. The final exam is going to be based on your 7% exams. So you're going to have a golden opportunity to basically redo those questions and get them right. So I've had a lot of people rally very nicely on the final exam. So even though it's a big ticket item, it's actually provided a lot of dividends for a lot of people. So yeah, these little 7% exams are, will there be, yeah, let me say the 7% are almost like quizzes. Will there be a mastery exam study guide? Yeah, actually I will. I'll send you out a PDF. Um, I'll send you out a PDF in about a week or two, a few days before the mastery. And then Laura says, do we get to learn from our failures? Yeah, actually you do. You get a chance to redeem yourself. So it's pretty typical for students in this class to stumble around for the first 2/3, and then they start picking it up in the last third, and actually had some pretty good success rates overall. So I think you guys are doing all right, doing the right thing. You just got to hang in there. Okay. All righty. Appreciate the feedback. And you guys be safe. Continue to do your math. I'm going to post this to the video here in about an hour. And as usual, if you have any other questions, post them to Ed Discussions in the meantime. So this has been a Scott Surgeon production. Thank you very much. Bye.